Good afternoon and welcome to the last Spectrum Scale User Group digital event of 2020. In today's talk slot, we've got two talks today. The first talk will be from Michael Hennicky from Lenovo. Michael's going to talk about Spectrum Scale and NVMe storage. So Michael is Lenovo's chief technologist for HPC storage and networking, and he has over 27 years of experience in high-performance computing. Before working at Lenovo, Michael worked at IBM, where he was involved in GPFS from version 1.1, and worked on the early GSS storage systems as well. Lenovo evolved these into the distributed storage solution for IBM Spectrum Scale RAID. So just a little bit about the user group, if you don't know about us. We are independent from IBM, but we do work very closely with IBM to develop our events. And we have a number of speakers from IBM today later in the session as well. The user group's not a replacement for the PMR process. Although we do have a very lively email and Slack community. People do ask questions in the community in there. The website's there for you to find out and join if you don't know about that already. So the user group's made up of 5 users who help coordinate activity around the world. And we're all IBM champions, which means we're recognized for our contribution to the community for what we put in. And with this, I think I'll hand over to Michael to start his talk. Kedar, could you make Michael presenter, please?
Can you see my slides okay?
Yep. Yes, we can.
All right, so today I will talk about 3 different subjects that are all related to NVMe storage, and they are a little bit related, but really more or less individual items. The first thing will be trim. We had a few sessions already about what has been new features in the recent Spectrum Scale releases. I want to spend some time talking about the trim support that made it into 5.04, show some results, and also have some recommendations here on how this might be evolved further. Then in my second part of the presentation, I will present a NetApp all-NVMe box and how it can be used in the good old Spectrum Scale sound mode that we used quite a bit in the Fiber Channel days. And then the last part of the session will sneak in some alien content here. Deos is an emerging storage stack, and it is interesting to see how that can be integrated with the existing parallel file systems. There's some work on the Lustre side, and we on the Lenovo side have experimented with like what can we do with Spectrum Scale and Deos together, and where in the future we may also need some help from the IBM development team if we want to do more. So let's jump into the first topic, trim. I did put the problem statement here, although I believe almost everybody on the call here will be familiar with NAND flash storage, which is used in pretty much all SSDs today. So we have 2 big problems. One is that we cannot overwrite a sector in place, right? We really have to clear very large erasure blocks, which is slow, and you have to like save whatever was left in that larger block if you want to change something. And then the second problem is just the physical endurance that NAND cells wear out. And so you have a limited number of program and erase cycles. And the controllers in the NVMe or SAS SSDs do their best to do background garbage collection and wear leveling and all of those things that are needed for this type of media. One area that needs some help, where the controller and the disk needs some help, is that it really doesn't know what the file system has done with the sectors or the blocks, right? And which of those are actively in use and which are not. And giving that information from the file system to the device controller of the NAND flash device, that's the purpose of the trim command. Trim is an ATA term. If you use SCSI, that would be unmap, or in the NVMe world, that's a deallocate operation. What that does is it tells the drive which logical blocks are actually not used by the software layer that's sitting on top. This is something that the controller cannot derive. If we tell the controller this information, it can do a better job, which will help both performance as well as the garbage collection backend. And part of the garbage collection process is write amplification, meaning that the drive internally is actually doing way more I/O than what we as the application people think, because it has to move a lot of stuff around. So that's the purpose of trim. And now let's look at how Spectrum Scale has implemented that. And just as an aside, mean, this is something that A, the file system has to do, but B, the device also, of course, has to know how to interpret this. All of the internal Intel drives, for example, that we are using in many places do support this, whereas a lot of the RAID controllers have not had a very good record of adding trim support, so the RAID controller could pass this onto the devices in a meaningful way. And I had it on my intro slide. The spectrum scale RAID component as well also needs to do this in a different way. So what I'm talking about here is not for spectrum scale RAID, it's just for classical NSDs, if you will. So to set up trim support in scale, you need 2 steps. The first one is to specify on the NSD stanza, when you do create NSD, to specify a new characteristic, which is called thin disk type. It can have those 4 values here, halogen rect, no, NVMe or SCSI or auto. No is the default. NVMe is what I will be using here because we'll talk about NVMe drives. SCSI is essentially the same statement. Trim is supported, but the protocol is different. And auto is also what the name suggests. It's trying to auto-detect. In the 5.0.4 release, I think it was discouraged to use that. Now I think it's the recommendation from the IBM team to use auto. But in our case, since we know we only have NVMe drives, we just set this to NVMe. So you do this in your stanzas when you create the NSDs. And then the second step is, and that's important, there's no automatic space reclaim in Spectrum Scale right now. So if you want to use this trim facility, you actually have to call a command called reclaim space. You give it the file system name, and then some other parameters, if you will, like you can restrict it to a pool, or you can set the QoS level. And then the mandatory argument in normal operation is the reclaim threshold. If you set that to 0, everything will be reclaimed. If you set it to 100%, essentially nothing will be reclaimed. So that allows you to control how much load you will have on the system, because this is what's used to be called an I/O heavy operation. Right? This is really sending a lot of commands to the disk drive, so it does impact user workloads a little bit. All right, point that to the documentation that will be in the slides. Just for reference, the server we are using here on the Lenovo side, we call it the DSS-G100. This is an NVMe-rich 1U server. Standard 2-socket servers with 8 disks, 8 NVMe disks in there, all of them 1.6 terabyte. And that's where we will run our experiment on here that I'm showing. I did capture some screens on just showing the command in action. So on the top here, we just see a freshly created file system, which has a single server, those 8 NVMe drives. It's 2% used. That's just the metadata that's sitting in the same pool. It has the correct version, 5.0.4. It has the disks displayed, ones from the MMLS disk command, and then below that, the NVMe list command shows you this is actually 4 Intel branded drives and 4 Lenovo branded drives, but all the same physical drive model. And then right after file system creation, of course, everything is free. So now if I run reclaim space, file system name, reclaim threshold 0, Spectrum Scale will reclaim the whole space. And you see in the DStat output below some really fancy numbers. Those drives can do 3 gigabytes per second, and you see they are doing 160 now. This is just DStat interpreting the reclaim space commands. So if you see that in your DStat output, you know that it's working, right? It's sending a lot of trim commands to the devices, and this is viewed by the operating system as a super linearly fast I/O on the disk drives. This whole operation on a single server with 8 of those NVMe drives took around 20 seconds to complete, and then we have wiped essentially all of the contents. I've told the controller it doesn't need to save any of that data. Now, the first thing that I wanted to highlight here, and we can have some offline discussion later on this, if I scale out my cluster, like what you would normally do in a bigger Spectrum Scale environment, now I'm running the same thing with 4 nodes, so 32 NVMe drives, same procedure, create the file system, then run the time reclaim space. Now it takes 1.5 minutes, almost 2 minutes. That's something that I believe warrants some investigation. We should be able to do this in parallel on all the drives, right? Because there's really no dependency between the individual nodes. Something is limiting the rate at which Scale is sending trim commands. to those devices. And I mean, if I look at this from a like high performance scale out perspective, it should be more parallel. It should also take 20 seconds, right? Because we can run on each server in parallel. So that's one observation that we found a little unusual, and we'll make more tests. We have a little more hardware, and we can scale this up to bigger numbers and see how that scales. But in general, like from a feedback perspective here, first of all, we have used this routinely in our benchmarks, and especially if our application specialists ask for storage exclusively, before we mount it on the application nodes, we now always run this reclaim space. So they start with a fresh SSD pool, if they will be, to get best performance. As I mentioned, performance scaling is something we'll have to look in. What I would personally also like to see is to make this the default when you do an create NSD or an create file system. I mean, the NSD is fresh. There's really no reason, from my view, not to reclaim space. So I would like Spectrum Scale to behave like, for example, XFS does. If you don't tell XFS anything, it will do a trim on the whole device. You have to actually say make fs-k in the XFS side to tell it to not do it. So that's something I definitely would like to see here in Scale as well. It is possible, but you always have to think about manually invoking this command, and it would be just nice if it happens automatically. Now, you could do more, and that's certainly something we need some conversation on what other side effects that had. But now everything is explicit. You have to call this command. It would be nice to have some administrator level control. For example, we could configure like an change config tunable saying whenever you delete a file, not just like free the block allocation map, but actually also send the trim commands for those blocks to the devices. That if the administrator can configure that, I don't see a drawback. People who don't want that could just leave that at no, and people who want space to be reclaimed could just set that to yes. So that would be a possible like improvement for future releases, or like even more automatic. There could also be a periodic reclaim, but that is certainly a little more difficult to get right if you have a very mixed environment. But like, overall, I mean, we're happy that we have this feature. It's a good addition, especially if like we are doing this. We are in a mode where you have a lot of very varying workloads, but people normally use those devices as stretch devices, and they want the best performance for their job, and then it's fine to erase things afterwards. And the reclaim space command is a natural addition after freeing up the file system space. So that's topic number one. And if there's questions in the chat, let's keep them for later on. Let me move to the next topic, the NetApp EF600. This is a NetApp box that we don't have in our portfolio yet. We're just working through the details here. We OEM in most of the NetApp E-Series portfolio, but this box is pretty new and it's not yet on our list, but we have it in our lab, and we intend to onboard that because we see there's good use cases for this. I just listed the specs here. The interesting stuff is not so much the performance. The interesting stuff is the fact that the host ports on this NetApp E-Series controller are all NVMe-over-Fabric. We attach them to InfiniBand, and we can use it to cut out the NSD servers, essentially, and go back to this SAN mode that we had, this fiber channel. And I'll just go through the steps that are required to do this. And there's the NetApp guide that describes the box in more detail, which will be in the slides. So just to recall the different architectures that we have in Scale. This is what almost everybody does today. It's the NSD client server module. The model, you have the disks attached to a small number of NSD servers through some sort of point-to-point or SAN, and then you have many more clients sitting on the LAN that are acting as NSD clients. But the people here old enough will remember that there was a time when we had the Spectrum Scale SAN model in more active use, where you had a fiber channel SAN, all of the storage was on the fiber channel SAN, and all of the GPFS nodes were also on the fiber channel SAN. You did not need NSD servers because all the GPFS node had direct visibility to all the NSDs. And that was quite useful in like not the massively scalable systems like the very large HPC centers, but in particular in commercial environments, in more data analytic focused environments. And what we can get now with this NetApp boxes, we can actually use this model, but instead of fiber channel, we're using NVMe over Fabrics, and we typically have an InfiniBand fabric anyway. So scaling in the fiber channel world was, I think, around 64 nodes. We actually have more than that on our InfiniBand fabric right now in our lab. We haven't scaled to thousands, but we have scaled to 100, and it looks reasonably robust, and it gives us some performance advantage in some areas. So the first thing to note when you set up this box is, in addition to the 2 IPs that you need for the A and B controller, which are in orange here, you also will need an IP over IP address, essentially, for each of those 8 host ports, which are all InfiniBand. Essentially, each controller has 2 dual-port InfiniBand cards, so 8 ports in total. They all need an IP address. You need that to talk to that from the host side. These are the blue numbers here. And then on the E-Series or Lenovo DE series storage manager, many people will still know the SM-CLI commands to configure those systems. IBM has them also, or had them as the DCS series storage. Normally, when you map a LAN to your SAS or fiber channel host ports, you create a host group, then you add hosts to that host group, and then you add a host port to the host. And in the traditional world, the host port is a SAS or a fiber channel port. There was also an iSCSI version, and the syntax here is very similar to iSCSI. So the only difference to the normal E-series setup is really you create an initiator. The initiator gets an identifier, which is this NVMe-over-Fabric NQN UUID, and that UUID, you can find that in the file in the host if it has set up NVMe-over-Fabric. One small issue is that this is actually not persistent. If you reboot the host, that UUID changes, and then you have to redo the mapping on the EF600. That's something that we have been fiddling around a little bit. If somebody knows how to make this persistent, get in touch after the call here. I'd be very interested. Now, on the host side, there are 2 steps. You have to do an NVMe discover step, and you give this NVMe discover the target IP address of one of the host ports of the E-series server, the E-series controller, and it responds with a lot of information, including the storage subsystems NQN name, and you need that later for a connect operation. You do that for all 8 ports if you have all 8 connected, and you should get the same UUID back because you're always talking to the same storage system. So they should all respond with the same NQN number. And then in the second step, at the bottom of the page here, you have the NVMe Connect operation, and you hand this connect operation the NQN ID of the NetApp box that you just received through the discover operation. And again, the IP address of the controller port, and what we do in operation normally is we increase the queue depth and we increase the controller timeout session, so there's enough time to handle path failures and that. And that's it. You should have a connection now through typically the one RDMA port on your client node to all of the RDMA ports of the storage system, because that storage system is typically connected into our InfiniBand fat tree. And that's maybe worth noting. If you read the NetApp documentation, they are actually using InfiniBand switches in their documents like they would use fiber channel switches. So like redundant pair of switches and cabling, just like you would do with the fiber channel SAN. But in an HPC world, we have a fat tree, right? And we just put the EF host ports somewhere on the leaves of the fat tree, just like we would do our compute nodes, and it works just fine. There's nothing special. It worked out of the box. We had some concerns initially if that would be something that is supported or works, but no issues. So you just hook it up like you would hook up compute nodes. So now every server, every compute node that is on the fabric can see all the 8 host ports if you have connected all the 8 host ports of the EF600. And then some other fancy things. The NVMe command has a NetApp sub command, so you can do NVMe NetApp SN devices. What you see here, that the device number, so NVMe 1, 2, 3, 4, 5, actually corresponds to the host ports of the EF, and the volumes that you have mapped on the storage system correspond to namespace IDs. So in this case here, we have 2 namespace IDs, 1 and 2, because I only mapped 2 LANs, and we have a total of 4 NVMe devices, because to make it easy and make it fit on the page here, we only connected 4 of the 8 host ports of the EF system. I personally would have thought that this is the other way around. So it's a little unusual at first, but after a while, you just internalize that the namespace ID is the volume and not the device ID, which would be more natural in a local NVMe device. So this command also tells you the name of the volume on the storage system, which is convenient when you want to name your NSDs like how they are named on the storage system. And one final step in the setup is you will be using normal device mapper multipass to manage failover across the InfiniBand links on the storage system side. I mean, on the host, you typically have only one link, but you have multiple paths to choose from through the InfiniBand fabric. So if you install this standard multipass.conf file for the EF600 and you do a multipass-ll after that, you get what you expect. I have 2 volumes, and they are now called DM1 and DM2. And under each of them, I have 4 paths, 2 of them with a higher priority, that is the active NetApp controller, the A or the D controller. And the other controller has a lower priority of 10, so it will only use those paths if there's a controller failover within the storage subsystem. So that's working out of the box as soon as you have the right multipass.conf in your setup. And the exclude at the bottom here is just for us locally, because we have some NVMe drives in the nodes themselves, and we want to exclude them from the multipass. So all in all, this is a very nice feature that allows us to run workloads talking directly to the NSDs. There are some workloads where Spectrum Scale really doesn't do a very good job when you have NSD servers, because the NSD servers are stateless, and they are, if we can avoid the NSD server in the data path and just have the application nodes talk directly to the storage, those workloads get a significant improvement in performance. We have run some of the IO500 stuff on the box, but we haven't completed a fully valid IO500 run yet because there were some other issues in the system, but we intend to do that and then compare that with the system where like you have the same storage hardware in the back end, but use NSD servers in between. And in particular, stuff like the IOR hard, the 47 kilobyte reads and writes, performs almost an order of magnitude better on this box than if you would do it with an NSD server. All right, so that's a good addition to the portfolio, I would say. If you want a block storage controller type storage system, but also want end-to-end NVMe, then the EF600 is a very good fit. There's a smaller EF300 version, but for like high performance workloads, I don't think that's a good fit in our like Spectrum Scale environments, but the EF600 definitely is. All right, so let's spend the last few minutes here on a topic that may be new to most of you. Deos is a storage stack that is developed primarily by Intel. It will debut at large scale at Argonne in our Aurora system next year. And it is an object store that is built on top of storage class memory. Right now, Optane persistent memory from Intel. And the bulk storage is NVMe storage, and there are no disks in this system. Right? They're only using SPDK and PMDK as the framework to talk to the devices. Deos itself is essentially a key value store, and then you can have pools of storage, and in those pools you can create containers of multiple like internal formats. There are HDF5 containers, there are normal POSIX containers, and what we started with experimenting in the context of Spectrum Scale is to mount the Deos POSIX containers within Spectrum Scale and use some of the features that we have in Spectrum Scale. And the same activities are happening on the Lustre side as well. So from a hardware perspective, the server looks like just like our G100, with the exception that Deos relies on storage class memory. So we have the Optane PMEM modules in the server. Otherwise, it's the same box, and we're installing it with the same installation toggle as we install our DSS-G100. Now, although this has been built to avoid or circumvent limitations in POSIX, of course, everybody has POSIX applications, so there has to be sort of compatibility layer. This is implemented in the Deos libdfs library, which is very, very close to POSIX. And there are a number of ways you can use that. If you don't want to modify anything, Deos ships with a diffuse daemon, and you can just use a user space mount, but that has not a very good performance. The second step would be you can overload with an LD preload all of the POSIX calls, and they would be rerouted transparently to libDFS. That's number 2 here. That gives you already very good performance for like data-focused workloads, but of course, all the metadata still goes through diffuse, so that will not be very fast. If you want good metadata performance on a POSIX-like workflow, the application would need to be changed to directly call libDFS. So that's the 3 stages of POSIX integration that there are in Deos right now. And the interesting thing is now to use this, you have to diffuse mount as a user your container. And let me go to the next page here. There's a lot of stuff on here. In essence, when the storage administrator provides me Deos storage, they give me a pool UUID, which is like 4 servers of NVMe storage, for example. When I have rights for this, I can create containers in that pool as a normal user, non-root user, and I get container UUIDs back. Let's say I have a POSIX container and I want to use that. Then if I don't have namespace integration with other file system layers in the Linux operating system, every command that I carry out has to carry around this -- pool and -- container, and also the -- SVC that's grayed out here, but that will disappear in the next release. So the first convenience function that Deos offers is that you can actually store those pool and container IDs in extended attributes, and then instead of carrying around those unreadable UUIDs, you can just use the path name of the mount point directory, and Deos will be able to retrieve the extended attributes and then know which pools and which containers to mount. And we've done this with Spectrum Scale, and it works with 1 or 2 minor glitches. It works just fine. So the Deos command would be Deos container create. You give it the pool that already exists, and then either this command picks a UUID for the container, or you can also prescribe a container UUID, and you give it the mount point path. In this case, in my home directory, there's an empty Deos TMP, or there will be created an empty Deos TMP directory. And if I look at this directory after Deos has created the container with the mmls attribute command, or with the standard POSIX standard attribute tools, they work as well, you'll see that Deos has stored a URL or URI as an extended attribute. It's at the bottom of the page here saying deos.posix : // and then you see the pool ID and the container ID. And from this point on, now if I'm back in Deos world, I can query the container just using the GPFS mount point, and it will retrieve the extended attribute and then know about the pool and container, and can use other Deos internal mechanisms to get to the rest, like the number of snapshots and all the other information here. And when I mount, I can also just mount this directory. So that integration works out of the box because it's just essentially POSIX external attributes. What we also would like to do is to provide a link into the other direction. So when, for example, the user has moved this mount point, then Deos, of course, doesn't know about that. It knows about the mount point that was specified at the container creation, but users can do all kinds of creative things with this, right? And there you have no way to track it. In Lustre, there will be essentially changes in Lustre to point into the other direction, so Deos can maintain consistency with those informations, even if the user has changed the path to this. The other area where it's interesting to look at tighter integration is, for example, if you're using HDF5 containers, those are now no longer directories, right? They're not POSIX containers. They actually have like more sophisticated internal data structures. And on the Lustre side, they can transparently essentially open that and present the contents of this. That will, of course, be not that easy in Spectrum Scale, and it's questionable if there's enough value in that to look at sizing the effort and doing that. But at least we're experimenting with the stuff on the POSIX side that is like easily accessible without doing any changes in Spectrum Scale. And stuff like immutable files and this pointing back information, like inodes from the GPFS side, storing them in Deos, that's stuff that we're actually investigating and developing right now. And I think that's it. I have some IO500 numbers here and some references if you want to learn more about that solution, but it's really like complementary to Spectrum Scale. I just wanted to show, because we also showed that in the Deos user group, that there is some potential to integrate the two worlds. With that, I'm done. I thank for your attention, and back to you, Sam.
That's great. Thanks, Michael. if people have got questions, there is a Q&A box in WebEx that you can use. I can see there's a couple that have been asked and have already been answered, which is handy. I was just checking anywhere else if anyone else has got any more questions. If not, okay, thank you, Michael.